This kind of small animals is our familiar neighbors in Hamilton. You can see at least hundreds of them searching, jumping, and climbing. These cute small animals move by jumping. Have you ever discovered that their jumping method just like a continuous oblique projectile motion? Since we all like squirrels, we decided to study how squirrels moving, what is the initial velocity and jumping angle, also how many works and power they do during the motion.
Assuming the squirrel's jump is similar to that of a projectile's, we can determine its speed, the angle which it jumps, and the work and power done by the squirrel. When recording the squirrel jumping in the grass, we determined its distance, time, and height. The distance recorded was 0.6 meters, the time taken was approximately 1 second, and the height was 0.25 meters. Since we could not catch the squirrel for fear of contracting rabies, we searched online and assumed the squirrel had a mass of 0.5 kilograms. Also referring to online sources, we found the coefficient of friction for grass to be 0.35. Calculating the squirrel's speed. Using the energy method, we are able to determine the squirrel's initial speed before it takes off from the ground. Before jumping, the squirrel has a maximum kinetic energy value, but zero potential energy. At the maximum height of its jump, or the height at half the distance it jumps, the squirrel has zero kinetic energy but maximum potential energy. Using this concept, we can solve for the squirrel's speed. Using the equation for kinetic energy, K is equal to mv squared, and the equation for gravitational potential energy, U is equal to mgh, we can equate them. When doing so, we end up with h is equal to v squared over 2g. Masses cancel out. Since we are trying to solve for the speed, we can isolate the variable v and plug in our known values. We obtain a speed of 2.21 meters per second. Calculating the angle of the squirrel's jump. Using our beautiful trig ratios, finding the angle is easy. We know the hypotenuse to be 2.21 meters per second. We can easily calculate the speed in the x direction by using v is equal to d over t. The distance traveled horizontally is 0.6 meters, and the time taken is 1 second. Thus, our Vx is given as 0.6 meters per second. By using cosine, we get a value of 74.25 degrees. Calculating work and power. To find work and power, a few pre-calculations are needed. We know that work is given as Ft cos theta, and power is given as work over time. The last piece of the puzzle is to solve for the force acting on the squirrel. The angle of the squirrel's speed is the same as the angle of the force acting on the squirrel. From here we can say that the net force times the cosine of the angle is equivalent to the friction force acting along the x-axis. Friction is given as mu mg. Mu in this case is the coefficient of friction for grass. Thus, when we put everything together, we get F net times cosine 74.25 is equal to the friction force. When solving for the net force, we get a value of 6.318 newtons. From here, it's all just plug and chug. Our work equation spits out a value of 1.029 joules, and our power equation coughs up a value of 1.029 watts.
Why can squirrel jump so far? In the video, we measure that it takes very small energy for a squirrel to jump such a far distance. Squirrels have relatively small and light bodies, but they have very powerful hind legs, much larger than their front limb, which give them a strong propulsion force to jump for a far distance. Second, the wrists of squirrels' hind legs are double-jointed and hyper-extendable, so that they can reverse pond directions and run down a tree as easily as they run up. The sharp claw also let them find a secure jumping point on a flat surface. This gives squirrels a firm jumping-off place from which to start a vertical leap. These physical properties, like small sharp claws and visible hind legs, squirrels can also end up set down when they run on the tree.